let's talk about a very important class of series that will come up again and again in our future sections. These are P-series. So, definition, a P-series is any series of the form the sum as n goes from 1 to infinity of 1 over n to the p power, where p is any real number. So note here that the p is fixed for a given series. Let's look at some examples of what's a P-series and what's not. So here's some examples. What if p equals 1? Well, then we have the series, the sum, as n goes from 1 to infinity, of 1 over n to the 1, which is just 1 over n. We already know this series. We're quite familiar with it. This is the harmonic series. Another example, what if p equals 2? Then we'll have the sum, as n goes from 1 to infinity, of 1 over n squared. This one we've looked at in class. This is also a P-series. In fact, we talked about this and we used the integral test to determine that this series converges. And we've discussed in class that the sum of this series is pi squared over 6. The proof of that is beyond the scope of this class, and we're not going to talk about it in this class, but it's interesting to note that it's there. And of course, the harmonic series diverges. We've already proved that as well. Here's another one. What about the sum, as n goes from 1 to infinity, of 1 over the square root of n? Is that a P-series? Well, yes, it is, because this is the same thing as the sum, as n goes from 1 to infinity, of 1 over n to the 1/2 power. So this is a P-series with p equal to 1/2. A few more examples. What about the sum, as n goes from 1 to infinity, of, let's say, n? This is a P-series. This is the same thing as the sum, as n goes from 1 to infinity, of 1 over n to what power? Well, if the power is -1, then 1 over n to the -1 is the same thing as just n. This is a P-series with p equal to -1. And similarly, we could have the sum, as n goes from 1 to infinity, of n squared. Here the p is equal to -2. You could have n cubed, you could have n to the 4th, etc., and to any power you want to. But since the p, by definition, is the power that's on the n in the denominator, that means that if your n is in the numerator with a positive power, it means that your p is actually negative. We use this notation because the series that are most interesting to us are the ones where the n is in the denominator with a positive power, and therefore your p is positive. These series that I'm writing down here are less useful and they come up less in conversation, and we'll see why in a moment. How about this series? The sum, as n goes from 1 to infinity, of 2 to the n. Well, that's not a P-series. The function that describes the terms of the series is 2 to the n power, which is an exponential function, rather than 1 over a power function, or a power function. So this is not a P-series. Actually, it's a geometric series. So here's an important question. For which values of p does a P-series converge? We already have some answers to that question. Some of the examples that I just showed you are series we've already examined, and we've determined that the harmonic series diverges, for instance, and the series, the sum of 1 over n squared converges. But in general, what can we say? What values of p are going to cause the series to converge? Well, first thing to think about, well, if p is less than 0, then you're going to have the sum, and n goes from 1 to infinity, of 1 over n to a negative power, which is the same thing as a sum, as n goes from 1 to infinity, of bring n to the top, and that'll have a positive power. We just talked about that. If your p is negative, that means you have n in the numerator with a positive power. Now, will any of these series converge? Well, no. The test for divergence says the limit as n goes to infinity of n to a positive power is definitely going to be infinity, not 0. Remember, the test for divergence says if the limit of the individual terms is anything other than 0, then your series diverges. So, the p-series will diverge. So, if your p is negative, that is, the power on the n in the denominator is negative, then your p-series will diverge. What about if p equals 0? Well, then we're going to have the sum, as n goes from 1 to infinity, of 1 over n to the 0, but that's actually just 1. So what are we adding up? We're adding up 1 plus 1 plus 1 plus 1 plus, etc. That definitely diverges. So put these together. That says that if p is less than or equal to 0, the series diverges. So what if p is greater than 0? So if p is greater than 0, then what can we do? Well, some specific cases we've already studied. We've looked at the case where p is 1. Then we had the harmonic series, and that series diverges. We've also looked at the case where p is 2, and determined that series converges. But there are infinitely many real numbers that p could be, and we don't have time to check all of them individually. We need to do something more clever. So let's note the function f of x equals 1 over x to the p power, where p is positive. This is a function that is continuous. It'll be continuous everywhere except when x equals 0. It'll be continuous for all positive values of x when x is greater than 0. And it's also positive because as long as x is greater than 0, then any power of x is also greater than 0, and 1 over that's also positive. So positive when x is greater than 0. And furthermore, as long as that p is positive, that means that the bigger x gets, the bigger your denominator gets. Right? Any positive power of x, the function is going to increase as x increases. But 1 over that denominator, therefore, is going to be getting smaller. So this function is actually always decreasing. As long as that p is positive, this is decreasing when x is greater than 0. So therefore, in fact, we can say this is true on the interval from 1 to infinity. These are the conditions that we need in order to justify using the integral test. So we can use the integral test. As long as these three conditions are met, we can use the integral test. So instead of trying to find the series, the sum as n goes from 1 to infinity of 1 over n to the p, let's find the integral from 1 to infinity of 1 over x to the p power dx. And let's figure out what the value of this integral is. So let's figure this out. I'll start by just rewriting my function here. So this is equal to the integral from 1 to infinity of x to the negative p dx. Now, the antiderivative here, therefore, is going to be x to the power of negative p plus 1, I have to raise the power by 1, divided by the new power. So, in fact, we can call that 1 minus p instead. They'll go from 1 to infinity. Now, we said that our p is greater than 0. We've made that assumption. And that's fine. But what happens if p equals 1? Then we can't divide by 1 minus 1. That would be 0. That doesn't work. So this is true if p does not equal 1. If p does equal 1, well, then that means we actually had 1 over x as our function, and therefore the integral is actually the natural log of the absolute value of x. So either way, any value of p that we have, we can integrate this. We'll get different results depending on the value of p. So let's break this down. We had the case where p was equal to exactly 1. Then the integral from 1 to infinity of 1 over x to the 1 dx is equal to the natural log of the absolute value of x going from 1 to infinity. Now this is going to give us the natural log of infinity, essentially, minus the natural log of 1. But that's going to infinity. So this integral diverges. So the p series, sum of 1 over n to the 1, as n goes from 1 to infinity, also diverges. Well, guess what? We already knew that. This is the harmonic series we already knew. We determined by other methods that the harmonic series diverges. It's nice to have it confirmed using the integral test. What about the next possibility? What about the case where p is between 0 and 1? Well, then we know the integral from 1 to infinity of 1 over x to the p dx is giving us x to the 1 minus p. We raise the power by 1 and divide by the new power over 1 minus p, going from 1 to infinity. So let's actually do this properly, take a limit this time. This is going to be equal to the limit as t goes to infinity. I'm changing my variable to t now, just to keep things straight. I don't want to use x here. Of t to the power of 1 minus p over 1 minus p minus, now I'll plug 1 in. Now 1 to the 1 minus p power, that's just 1. And that's over 1 minus p. So what's going on with this limit here? Well, this is very important. Because p is less than 1, 1 minus p is positive. And since 1 minus p is positive, that means we're having t to a positive power and letting t go to infinity. That means this whole thing is going to be infinity. So this again diverges. And therefore the p-series diverges. One more thing to look at. What happens if p is greater than 1? So this time the integral from 1 to infinity of 1 over x to the p dx, again, is giving us x to the power of 1 minus p divided by 1 minus p, going from 1 to infinity. Same as before. This integral gives us the same result, the same formula for the result, any time that your p is not 1. And this is going to give us the limit as t goes to infinity of t to the 1 minus p over 1 minus p minus 1 over 1 minus p. What's happening this time? Well, this time p is greater than 1. Now, so if I say 1 minus p, 1 minus a number bigger than 1, that's negative. Since p is greater than 1. And t is going off to infinity, but you're taking t to a negative power. So essentially, it's like you're dividing by t a lot of times. Well, if t is going to infinity and your t is being taken to a negative power, that's going to approach 0. So this limit is actually 0 minus 1 over 1 minus p, whatever that happens to be. That'll actually end up being a positive number because 1 minus p is negative and you're subtracting that result. That's a positive number, but the important thing is it's finite. So this integral converges. And therefore, the p-series also converges. So to summarize, we've just figured out what happens to every possible p-series for every possible value of p, which ones converge, which ones diverge. What we figured out is that the p-series, sum as n goes from 1 to infinity of 1 over n to the p power, converges only when p is greater than 1. And it diverges for any other value of p when p is less than or equal to 1. Let's apply this to some examples. So when p equals 1, we get the harmonic series. The sum as n goes from 1 to infinity of 1 over n. Now, we already proved that that series diverges. But it's nice to have that confirmed by a different method, by the integral test. When our p is equal to 1, 1 is, of course, less than or equal to 1. So, according to our theorem, the p-series should diverge in that case, and we already know that it does. When p equals 2, well, 2 is greater than 1. So our theorem says the series should converge. And we already figured out this series does converge using the integral test. What about this last series here? The sum as n goes from 1 to infinity of 1 over the square root of n. Well, that is a p-series with p equal to 1/2. Does that series converge or diverge? Well, p is equal to 1/2. That is less than or equal to 1. What this is basically telling us is the denominator of the terms here is growing as n grows, but it's not growing very fast because the square root function doesn't grow very fast. And what that means is that your terms are shrinking as n grows, but they aren't shrinking fast enough. They're not shrinking fast enough to give us a finite sum. So, according to our theorem, this p-series diverges. How about one more example? The sum, as n goes from 1 to infinity, of 1 over n to the pi power. Well, pi is greater than 1, so this p-series converges.